This is an AQA A-level chemistry topic. It's from year 13, it's organic and it's amines. I'm going to recommend, as always, that you pause and have a go at the activities for yourselves to see how confident you are on different aspects of this topic. In this first video of 3, we are going to introduce amines. We're going to look at how we name them, we're going to look at some of their reactions, we're going to look at what an amine actually is. Now, the examiner's tip here relates to primary, secondary and tertiary structures. You've come across those before with carbocations, and we're going to use that same terminology again. So let's begin with some of the more straightforward work. In part, goes back to GCSE. What would the dot cross diagram for ammonia look like? Well, we have got a nitrogen and 3 hydrogens. Its formula is NH3. Each of the H's has 1 electron and needs an extra one, so it puts 1 in for sharing. When it comes to the actual structure in terms of nitrogen, the way that I would always look at this, and you can look back at the bonding videos in the year 12 playlist if you'd find that helpful, but nitrogen, I'm going to look at what group it's in. It's in group 5. If it's in group 5, how many electrons in its outer shell? It has 5. How many does it need to gain to get a full outer shell? It needs to gain 3 more. So how many bonds will it form? Well, for every bond you form, you put 1 electron in, but you get 1 electron back. So it's going to form 3 bonds. So it's going to put 3 of its electrons in, 1 with each H. It's in group 5, that means that it's got 2 more, and I'm going to put those as the lone pair up here. Now I am going to show you the alternative. You'll often see it with the rings drawn out. Equally valid, you can do it in either of those 2 ways. Now let's move on and do a little bit of recap work from the bonding topic. What would the 3D structure look like? What would we call the shape? And what would the bond angles be? Well, to start with, we have got 4 pairs of electrons. That means that it's based on tetrahedral. Within that, it's not actually 4 bonding pairs. It's got 3 bonding pairs and 1 lone pair. We actually just saw that here. 1, 2, 3 bonding pairs and 1 lone pair. So, with that in mind, based on tetrahedral, I'm going to start by drawing out my structure. We were specifically asked for 3D, so I have shown the line going into the paper, the wedge coming out of the paper. To represent my lone pair, I've got to remember to include the cloud, the rabbit ear on the top, and I have now got the structure drawn out exactly as we would want it to be. Now the shape is based on tetrahedral, but you also have to remember its specific name. This is trigonal, that's related to 3-point, pyramidal, that's related to pyramid, and we've actually got a 3-point pyramid that you can see here, and I'm just going to draw this in. You can actually see the pyramid shape. In terms of the bond angle, well, you've got to remember the bond angle is 109.5 degrees for tetrahedral, and a lone pair will take 2.5 degrees off, so the bond angle is 107 degrees. Still on recap of ammonia, what's the equation for the Haber process? What are the conditions? Why are they considered a compromise? Well, to make ammonia, we use nitrogen and we use hydrogen. We also have to remember that this is a reversible reaction. It's one of the most common questions or common reactions that we consider when answering questions about equilibrium. So we've got our reversible symbol there. We need to balance it. Well, I've got 2 N's, so I need 2 N's. And if I've got 2 N's and 6 H's, I now need 3 H2. I've also remembered to add my state symbols. In terms of the conditions, again, these are facts you need to remember. 200 atmospheres pressure, that's 200 times atmospheric pressure. That's 200,000 kilopascals. It's a very high pressure. It's also 600 Kelvin as a temperature. There's actually a range around that that's accepted, but 600 will get you it. And we use an ion catalyst. But then we have equilibrium-based questions. Why are these compromises? It's actually temperature and pressure that are compromises. Temperature is a compromise of yield versus rate. And more specifically, we can explain that the higher temperature would lower the yield. That's because increasing temperature would favour the endothermic reaction. In this case, the endothermic reaction is the backward reaction. But on the other hand, if I brought the temperature down, if I decrease the temperature, that's going to decrease the rate. So we've got to find the optimum temperature that will give us a good enough yield to maximise profit at a good enough rate that we will get that yield quickly enough. In terms of pressure, that is also a compromise, because increasing pressure does increase yield. That's because there's a reduction in the number of moles, 4 to 2. But actually, we would have to generate that pressure, and it's whether the increased costs of generating those higher pressures would be enough to make the extra profits from the higher yield worthwhile. The costs are partly about generating the pressure, but they're also about reinforcing the reaction vessel. If the pressure's higher, we need to make sure that the walls are thicker so that the vessel wouldn't explode when the reaction was taking place. So that would mean thicker walls, that would mean more material, that also means greater cost. So compromise is the key word in both of those things. Okay, let's move on. We're going to look again at familiar work going back to year 12 now, the reaction between ammonia and chloromethane. Well, let's draw out what we have. Have a think about what the mechanism would look like. What would we call it? What would be the nucleophile electrophile stroke reagent, whichever are appropriate here? And we'll see just how many marks we can get. Well, the key to this is to think about why there would be an attack. And I've got here a delta negative chlorine, which makes it a delta positive carbon. And I've got a lone pair of electrons. So my lone pair of electrons are going to attack the delta positive carbon. That essentially means I've created a bond between the carbon and the nitrogen, and that would mean 5 bonds around the carbon, which we cannot sustain. So we break one of those. The electrons in the CCl bond move off with the chlorine, essentially breaking that bond. That takes us to our intermediate structure. You can see my NH3 has essentially substituted where the Cl was. The Cl minus has come off separately. But there is something missing here, because this N has got 4 bonds around it. Now, if you think about ammonia becoming an ammonium ion, we can bring on an H+. In this case, we've brought on a CH3+. Overall, it means that this is a positive ion. We put a plus sign on the nitrogen. You miss that and you lose marks. There's now a second step to this mechanism. I've got 1 mark, I've got 2 marks for the 2 arrows. I've got a 3rd mark for my intermediate structure. My 4th mark for the mechanism comes from recognising that we have ammonia, but this time acting as a base. So this now links to the acids and bases topic. A base is a proton acceptor. So I'm going to show my curly arrow going from the lone pair to one of the hydrogens. That then means that the NH bond can't exist anymore. So those electrons move in. That is going to discharge the nitrogen, take that down to 0. And we are left with our amine. You can see that's got a lone pair. That's going to be really important later in this topic. And we've made NH4+. So we've got 3 products here, if you look at it. We've got our amine, we've got our ammonium ion, and we've got our chloride ion. Well, the ammonium and chloride ions will combine together to make the salt ammonium chloride. Okay, let's go on to look at classification of amines. We see this with alcohols. More importantly, we've seen it with carbocations, and we can see primary, secondary or tertiary amines. And I'm going to start by highlighting the alkyl groups, because that is going to make this far more straightforward. Remember, if there were no R's, if they were all H's, it would be ammonia. But if there's 1 alkyl group, that makes it a primary amine. If there are 2, it's a secondary amine. If there are 3, it's a tertiary amine. Going to move on and look at nomenclature, and the nomenclature for amines can get a little bit more difficult. We're not changing any of the rules from year 12, but we are adding to them. Let's start though with a few examples. How are we going to name these? Well, if we go left to right, the first one has got the longest carbon chain is 1. That makes it methyl. It's got an amine group on the end, so that makes it methylamine. On to the second one, I've got a longest carbon chain of 2. That's an ethyl group, so that one will be ethylamine. The next one has got 3 carbons in a row. That's propyl, so that one is propylamine. And if we take a look on the next one, we can see that actually this is slightly more complicated. I have got an ethyl group and I've got a methyl group, both coming off the N. So we need to name this in a slightly different way. The first thing that we can look at, and there are a couple of different ways you can do this actually, but I've got my ethyl and my methyl both coming off the N, so I'm going to put those in. N ethyl, N methyl. We put the N in here to specify where the alkyl group is connected to. And we also then put them in alphabetical order. That one, by the way, is secondary because it's got 2 alkyl groups coming off it. All 3 of these are primary amines because we've only got 1. Okay, we've got some more complicated ones to name now. I'm going to colour code these so we can see the answers, have a go at naming them, and then see how you do. First thing I'm going to do is highlight the different alkyl groups coming off and where they are. So, and now I can classify them. So I can see here I've got 2 groups coming off the N. That's secondary. This one has 3. It's tertiary. This one only has 1. It's primary. This one has 2. Secondary. This one only has 1. It's primary. This one has 3. It's tertiary. Let's go through looking at the naming of them. Now what you can do here is take a base amine, and this one I'm going to say is propylamine. Now we've got an ethyl group coming off there. So we have got an ethyl group coming off our nitrogen in propylamine. So we say there's an ethyl group, but we put an N prefix in to show that that N has come onto the N. On to the next one, and we have got here 3 different groups. It's the tertiary one. We've got propylamine again, but this time we've got 2 methyls coming off the N, so that's dimethyl. We need to show that both of them are coming off the N. So we call this one NN, dimethyl propylamine. On to the next one. And this one is, it's been drawn as a cyclohexatriene, but it is there to represent a benzene ring. Now for this one, we use the phenyl prefix. There's more explanation on when we use phenyl and when we use benzene in the aromatics videos. But that one is phenylamine. We move on to the next one, which has got 3 ethyl groups coming off it. Now we don't need the N here because all of them are equal. All of them are coming off the N. So that one is triethylamine. The next one, moving on to the orange, slightly more complicated. I've got an ethyl group, but I've got a methyl group coming off the ethyl group. So I'm going to call that one methyl ethylamine. But you'll notice there's no N before the methyl. That would mean the methyl was coming off the N up here. Here we know the methyl group is coming off the ethyl group. And we know it must be coming off the carbon closest to the N, because if it went on the second one, it would be extended to a propyl. And finally, on the top one here, we've got a phenyl group and we've got a methyl group. So we have N-methyl phenylamine. Let's now have a go at drawing some. So what would these look like? So NN diethyl cyclohexylamine. Well, here is my cyclohexane, so my cyclohexyl group. There's my amine group coming off it, but it's NN diethyl. That tells me there are 2 ethyl groups coming off the N. So they go on there. That one is done. Let's take a look at tripropylamine. I will do this skeletally. All of these propyl groups are going to come off the central N. So I go 1, 2, 3, 1, 2, 3, 1, 2, 3, carbons in each chain. For the next one, N-ethyl, N-methyl butylamine. Well, I'm going to start off with my butylamine, but instead of it being NH2, that's going to need a methyl group coming off because it's N-methyl, and an ethyl group coming off because it's N-ethyl. But again, you'll notice that ethyl goes alphabetically before the methyl. The butylamine, as the longest carbon chain, has gone at the end because we're starting with the butylamine group. And finally, pentylamine, relatively straightforward one to finish off. I've got my pentyl group, I've got my N. This is a primary amine, so I put my 2 H's on. Right, making some links. So based on your knowledge of ammonia, attempt the following questions. Predict the shape of a methylamine molecule. Where are the lone pairs? What would the shape be? And what would be the RNH bond, where the R is a CH3 or an H? I'm going to start by drawing out the structure, and I'm going to put my electrons in so that we can see. We're interested in what's happening around the N. This obviously is a tetrahedral structure around the carbon. Carbon always forms 4 bonds, so always will be. But if I make the N the focal point, I can redraw that to show the N with 2 H's and a CH3 group coming off. Not quite drawn that fully 3D, that would be a dotted line. Now from there I need to remember to include my lone pair, and the lone pair must include the cloud shape. And this is similar to what we saw at the beginning of the video. This one is a trigonal pyramidal shape based on tetrahedral. Tetrahedral has a bond angle of 109.5 degrees. We're going to knock 2.5 off that because of the lone pair. Goes down to 107. Okay, let's move on and look at the ammonium ion, something that you are more familiar with. Well, ammonium, we've got an N surrounded by 4 H's. What's really important that you notice here is that this is a dative covalent bond. It's brought in an H plus ion to form that 4th one using the lone pair on the N. Because of that, that means the overall charge is positive, so I've added my square brackets. Now that means I've got 4 bonding pairs of electrons. That means the shape is tetrahedral. Because it's charged, I'm going to put the square brackets on there as well and show that that's positive. But fairly straightforward tetrahedral shape, bond angle 109.5 degrees. Okay, so what about a methyl ammonium ion? Perhaps a little bit more complicated, but an ammonium is N with 4 bonds around it. If there is a methyl group, we're going to put the methyl group coming off the N, and we have got 3 others here. Once again, that 4 bonds around the N tells us it's going to be positive. It's brought in a CH3 plus ion to complete that structure. The bond shape, therefore, or the structure, is tetrahedral, bond angle 109.5 degrees. Let's move on and look at properties of amines. So you might need to research some of these. You might need to be thinking about what you know from year 12. I've got here methylamine and ethane. Which of those would have the higher boiling point? Well, if I draw them out, I can see, hopefully, something that really stands out. And that's the type of intermolecular force they're going to have. This one will have hydrogen bonding. This as an alkane will only have van der Waals. Hydrogen bonding is a stronger intermolecular force. That will have the higher boiling point. What about dimethylamine and ethylamine? Well, if I draw those out, they've both got hydrogen bonding actually because of the NH bond. They have both got an identical MR. But this actually has a stronger dipole-dipole force. And that's to do with the fact that the N is on the end of the chain. Because the N is in the middle here, you are going to get a weaker dipole-dipole force. Now that means that this one would have the higher boiling point, the ethylamine. And let's take a look at another one, trimethylamine and 1-aminopropane. Well, if I draw those out once again, we can see here that we have got hydrogen bonds within this, the NH, but no hydrogen bonding within our trimethylamine. That means that this will have the higher boiling point. What trend in the solubility of amines exists and how do they smell? Some important facts for you to remember. Well, we will start with the fact that small amines are soluble. And actually the reason for that is that they can all form hydrogen bonds. Even though they don't have hydrogen bonds themselves within them, the N and the lone pair on the N can form a hydrogen bond with water molecules. That makes them very soluble. The problem is, as the carbon chain gets longer, it gets harder for those to squeeze between the water molecules, which is essentially what happens when we dissolve them. So anything above a chain size of 6 carbons would be insoluble. And then, how do they smell? Well, the shorter chains tend to smell quite similar to ammonia, but the longer ones actually take on the smell of decay or the smell of rotting fish. That takes us to the end of this video. Thank you for listening, and goodbye.